And my research, broadly speaking, is in planetary science and astrobiology. More specifically, I do climate evolution of Earth-like planets. So I use climate models, but mostly on other planets, although I've done a little bit of early Earth climate modeling as well. And I do this with an eye toward questions of habitability. How do planets gain habitability? How do they lose habitability? What do we mean by that anyways, is a really fun question. And in my career, I've roughly speaking been sort of half research scientist and sort of half time, averaged over decades, sort of half time involved in various education and public outreach activities. And I guess I've had a somewhat unusual career in that I was a faculty member for many years at a university, and then I was a curator at a science museum for many years, and then I had this kind of unusual appointment as the chair of astrobiology at the Library of Congress, and now I'm roughly half-time soft money researcher at Planetary Science Institute, and roughly half-time writing and speaking and doing other media things. And that mix changes depending on what grants get funded and what projects come up. So not a completely typical career, but it has allowed me to sample a lot of different environments, because I've been at a research university, I've been at a NASA, a government lab, I've been at private nonprofit research corporation, I've been at at the Library of Congress. So I've definitely sort of sampled probably more work environments than your sort of typical scientist does in their career. Not that I set out to do that, but that's sort of the trajectory I've followed. I've, yeah, as I said, I've always done a lot of public outreach and in various forms. And I guess I realized many years ago that that I was strangely equipped to talk about climate change, where as climate change became a more sort of culturally important issue, which sort of happened while I was in grad school. I finished grad school in 1989. And that was really when climate change was becoming a thing. I mean, meaning something that was being publicly discussed and, in the popular media, and politicians were debating it and so forth. And actually one of my mentors was Carl Sagan. And he was really the first person I ever heard talk about climate change in a public setting as something that society should be concerned about. And at one point I remember thinking, God, it's really weird. All these terms, these jargonistic terms and physical concepts, which I studied in grad school as what seemed like very arcane and esoteric things, words like albedo and energy balance. Now I'm seeing them in, on Time Magazine and Newsweek, and people are actually talking about the changing planetary albedo. And it's like, wow, that's something I studied in grad school, not thinking it was relevant at all to anything important culturally. And so one thing I've done for a long time is tried in various ways to make that connection to some degree in my research, but certainly in my public communication between what planetary scientists do and what the public, should know and be concerned about with climate, because there are certainly a lot of connections there. And I found also that there's some advantages in discussing climate from an angle, an entry point that may seem unusual or surprising to people. Because, you know, especially a topic like this becomes so culturally sort of hidebound, and people think they know where they stand and they know what they know, because it's not just a scientific question. It's connected with how we identify, what group we identify with politically, and all that. And so sometimes that makes it harder to have those conversations and harder to reach people. But because of that, if you come from an unusual angle, it can be useful. And I've definitely experienced that, where somebody doesn't necessarily think they want to talk about climate change, but they're really interested in space. And they think that's really cool. And they think other planets are cool. And then you sort of, it's not like you're trying to trick them, hopefully, but it's like simply that you enter into the conversation from a different point of view and from a common point of interest. You know, common ground is really important to find. And it's like, okay, maybe somebody doesn't agree with me about certain things, but we both are fascinated by some of the same things. And so it's just a different framing that can be valuable. So anyways, what I thought I would do this afternoon is give, for maybe the first hour or so, what I will call sort of a meta talk, which is that there's a talk that I've given, a public talk that I've given many times, and it's evolved a little bit over the years, about, I call it climate catastrophes in the solar system. And I use it to talk about sort of dramatic climate change on other planets and how climate works on other planets, but then also work Earth into that. And it's a talk that I give geared for the general public. But since my sense of who you are, of the audience today, and maybe not just audience, but fellow discussants, because I would like to have this become a conversation as well. But my sense is that you are mostly early career astronomers interested in sort of increasing your climate facility with talking about that and thinking about that and applying your expertise to that topic in different ways. And so that's my assumption. So what I thought I would do, and I did one version of this once, and I thought it went okay. I thought it went pretty well for the Astronomers for Planet Earth. And so that's my sort of model, but I'm going to change it up a little bit. But what I'm going to do is give that public talk on climate catastrophes in the solar system, but then comment on the giving of it while I do it. Sort of stop and say, so when I show this slide, I'm saying this because of this. So sort of give the annotation while I give the talk. And then I'm going to try that. And then I'll try to keep it mostly into the first hour, so we really have plenty of time. But the other thing that I'll say is that if you want to interrupt me, go ahead. Either, you know, if there's something that can wait till the end of my spiel, then hold on to it. But if there's something that you feel is, you know, going to illuminate or expand that part of the conversation, or you just can't wait, then raise your hand or type something into the chat. And if I don't see it, somebody else raise your hand to get my attention. And I'm okay to interrupt and go off on tangents. And then if I'm not getting anywhere, if it's really slowing us down, I might sort of retract that a little bit to get through. But go ahead and interrupt me if you want, I guess is what I'm saying. Like, as if, you know, it's so much easier to do this when we're all in a room, but you know what I mean? Like, it's like, if something's not clear or you think it would really help to expand on it, then go for it. Okay, anyways, I'm going to share my screen. Oh, host disabled participant screen sharing. Hello, host.
Okay, 1 second. Okay.
Try it now.
Mhm.
No, it's not letting me. Are you sure? Are you, wait. Oh, now it's letting me.
Right now?
Okay.
Perfect.
Yes.
Sorry about that.
Cool.
Take it away.
Yeah. Okay. So let's do this. And let's do this. Now, are you guys seeing my presentation or my presenter mode?
Presentation.
Okay. That's the one thing that I can never tell with PowerPoint on Zoom. Half the time it shows you the actual presentation and half the time it's presenter mode, and it seems random, and then I click a button, it switches. But you're seeing the full screen here. Okay, awesome. Yeah. Thank you. All right. So yeah, this is what I'm calling it, and it's based on, this is the title screen of whoops, is it going to advance? Oh, there we go. This is the title screen of the public talk that I've given, and this dates it because it says Denver Museum of Nature and Science, which is a job that I left about 10 years ago. I was the curator of astrobiology there. So I've been giving some version of this for a while. But this was, I think, the title screen of maybe the first time I gave it. And I start off by talking a little bit about the question of what is a climate model? You know, you've heard so much about these. We rely on them. We depend on them. We hope they're right. What are these mysterious things? And I point out that, you know, we don't have a crystal ball to see the future, but we have these tools that let us, given some assumptions, which we can test in a variety of ways, make predictions. And then we have various ways of validating and becoming more or less confident in the nature of those predictions. And one thing I sometimes also point out is that when you see some of these graphs, like we see here with different scenarios for the coming decades for the rest of this century, and there's the scary ones where the temperature get really high and the less scary ones where it doesn't get that high. But you see this slide B here, the scenarios for CO2 concentrations. What those are assumptions about human behavior. So the biggest source of uncertainty in our climate projections is not our ability to physically model the climate, although there is uncertainty in that. There are things that we are not completely sure about and areas that can be improved, but the biggest source of uncertainty is what we assume about human behavior collectively, how much we're going to keep emitting. That's why there's such a huge difference between the scary and less scary scenarios. And it's important to realize that it's not that the huge dispersion is not because we don't know what we're doing in predicting climate. There's a little bit of that, but most of it is because we don't know how to predict human behavior. And there's something actually sort of encouraging in that knowledge, because it's empowering if you realize that that's the biggest difference between the bad and less bad scenarios, is what we do collectively as a species. So I think that's just an important thing to keep in mind. And then I might talk for a minute about what climate is. And if you look it up in the dictionary, of course, you see several different definitions, but the important one here is that it's average weather over a region or a period of years, or in this case, the region is a planet. And enough said about that. And then I also, since I'm talking about catastrophes, I also make a point about the definition of that term, because for scientists, it's a little bit different. I mean, it often does mean something terrible or awful, but it also sometimes we talk about a catastrophic change, not even with a value judgment, just meaning that some state of some system changes rapidly and dramatically. So if there's a massive change in climate on an uninhabited planet, it's not necessarily a catastrophe in the horrible loss sense, but it's a drastic change in state. If there's a massive change in climate on an inhabited planet, it generally is a catastrophe. And then I just mentioned that we live in this extraordinary time when we really can look at the planets in this comparative sense. And this is fairly new within the last generation or two that we've had this ability. I might make a joke about Pluto wanting to get in the picture, and then I say, okay, Pluto, you can be in the picture. And then I say that a lot of the focus of what I am going to talk about, and in fact, the focus of a lot of my research has to do with the nearby terrestrial planets, because amongst all this wonderful diversity of planets that we've discovered in our own solar system, and now, of course, beyond our solar system, we only have 3 nearby examples of terrestrial planets with sizable atmospheres. And so for that reason, the comparison of Venus, Earth, and Mars is one that I find fascinating and that I've focused on a lot. And then I just talk a little bit more about comparative planetology and its power and beauty. And I use this example of a similar phenomenon that you can recognize on different planets, and yet look in the details at the unfolding is how particular to each of these planets. So that shows us there's a commonality in the overall phenomena that the universe likes to enact in different places, but yet the particular differences can tell us stories about what's happened, about the biographies of those worlds. For instance, here is a river system on Venus, a river delta on Venus, and one on Earth and one on Mars. And the commonality in form is striking. And yet, if you look in detail at what's happening, you also see that these are telling us very different stories. In the case of Venus, this is a planet that we know could not have had liquid water in the time that this river-like, this delta-like feature formed. And so we are pretty sure that this was formed by some kind of runny magma, some kind of lava that flowed over the surface, and yet made a form that's recognizable to us as kind of a river delta. On Earth, we see this same kind of form, and yet clearly this has been shaped by a phenomenon that's unique, as far as we know, to Earth, which is biology. This is, you can see, this is a particular place where there are mangroves and such, and sort of the geology and the hydrology and the biology are all interacting and sort of mutually shaping this environment. And then over on the right, we see what is also clearly some kind of a river delta on Mars, but it's also telling us that this is something that was ancient, because you see that it's superimposed by at least one well-formed impact crater and highly eroded in a way that's telling us that this was once a river delta, but hasn't been for billions of years. So this is telling us about a story about climate change on a planet that has had some similar activity to Earth, but has not in quite some time. So anyways, that's just a little spiel about comparative planetology in general. And then, of course, one mentions that it's not just our solar system anymore, that we've learned now about incredible richness of planetary environments in our galaxy. And so the solar system now serves as sort of ground truth, the ones that we can get up to closely to help characterize and contextualize the much greater wealth of knowledge that we are just starting to mine from exoplanets. And of course, climate science is integrally involved in our efforts to understand the environments of those worlds and which ones may and may not be habitable. And then I'll say something about what we consider the sort of classical habitable zone, and the idea that Earth gets enough radiation from the sun to maintain liquid water. And that's hasn't necessarily always been true for Venus and Mars, and certainly isn't for other planets far and wide and farther and wider. Depending on how much detail I want to go into, I might mention that the habitable zone can migrate through time as the sun changes, and so forth, and might get into, as you can see in this graph, that there are different stars that have different luminosities, and therefore that will affect the size and shape of the habitable zone. And then to expand on that a little bit, I'll just get into, again, what we sort of mean by climate in the very basic sense. And I'll talk about the concept of an energy budget, that for a planet, there's a certain amount of energy coming in from the star and a certain amount of energy being radiated out into space. And the balance between those two forms, can determine the temperature in a very simple way, and forms the climate. And again, here I'll probably mention albedo and say what that is. The example of the people huddled around the campfire is just sort of gives you an intuitive sense of this. If you're cold, you get closer to the fire. If you're warm, you can back off. And so this basic sense of an energy budget and a radiative center is something that you can relate to. Then depending on the audience, sometimes what I'll do is I make things sort of pseudo quantitative. If I'm talking to a public audience, I say like, well, these are equations which express the energy coming into the planet from the sun with this squiggly thing, this alpha that means albedo, and that it equals the energy leaving the planet. And T is the temperature. And I'll say, you don't have to understand this equation. I'll say this, to my public audience, but what you ought to know is that there is an equation that relates that scientists understand, and that of the whole range of things that we think we understand, and some of it is uncertain, some of it isn't. This is something that we've got. Like, if you tell me just an object and the amount of radiation coming in and it's albedo and nothing else is happening, I can predict the temperature and it will be right, because this is like basic thermal physics. So sometimes I'll do this like where I don't want to bamboozle if it's an audience that I think doesn't want to hear math, I'll still show an equation or two and say, this is an example of the kind of thing we can do with math. If you know this, then you can get this out. And so that's the sense in which I'll show this. I'm sorry, my font got screwed up here anyways, but that's the sense in which I'll show that this, the equilibrium temperature is, you can determine from the albedo and from the amount of sunlight coming from the sun. And then I'll go over, the sort of the basics of the greenhouse effect, which I don't think I need to do for you guys, but just because you all know this, but it just the atmospheric gases that are transparent to solar radiation and opaque in different amounts depending on the gas, to infrared radiation, and how that ultimately determines the thermal balance. And one thing that I often do is I then talk for a second about, well, what is a greenhouse gas? Why are some gases greenhouse gases and others aren't? That the major gases in Earth's atmosphere are nitrogen and oxygen, N2 and O2, neither of which is considered a greenhouse gas. And the trace gases of CO2 and methane and actually H2O are greenhouse gases. Why? And you can sort of say some simple things which are true, that generally the diatomic gases, just made up of two atoms, O2 and N2, are not greenhouse gases because they have sort of rigid, simple, symmetric structures, and they don't really have the same kind of vibrations, therefore. Whereas the bigger, floppier molecules of CO2 and CH4 have all these other modes where they can kind of bend and vibrate and do that and do the funky chicken or whatever. And just because of that, because of that basic, that's funny, Siri just thought I was asking her a question. I'm not talking to you, Siri. quiet. That she goes, I can search this for you on the web. I'm like, what? Just that basic difference between a simple diatomic molecule and a slightly more complex triatomic or larger molecule is often what makes the difference, because of the way they respond to radiation, and they can have those vibrational modes. And it's that those are the energies which respond to infrared light. So sort of on that level, I'm sure those of you who know much more quantum mechanics than I do, which is probably most of you, are like horrified by my simplistic discussion of radiation, molecular radiation physics here. But I think on that level, people can kind of go, oh, okay. So CO2 is a slightly more complex molecule with more modes of vibration, and that kind of makes sense. So I think I've found that people can relate to that. So then I get a little bit back into the comparative climatology, shows some awesome pictures, and just the fact that we now have landscape photography of these three worlds, and you show this sort of typical place on Earth. If you landed at a random typical place, it would look like this in the middle. And we have surface photographs of a few spots on Venus. Within the decade, we're going to do better than that, I think. This on the bottom is the first ever landscape photograph on Mars from the Viking 1 lander. And so these are real places that now we've been to and can study and learn from their similarities and differences. And then I might quickly show some data. This is a little bit too busy of a graph, but what I have, and I don't have it loaded up here, is a slightly more animated version of this, where I show this and then it kind of grays out the numbers that you don't have to worry about and focuses in on a few things. And the few things that I focus in are the fact that one, that Earth is a really unusual planet. Out of this trio of worlds, it's Earth that's the oddball with all that oxygen and nitrogen. That Venus and Mars have very similar atmospheres that are mostly carbon dioxide. That on Earth, you can see that carbon dioxide is a minor gas. Can you see my cursor if I'm doing this? Moving? Yeah, okay. So on Earth, you can see that CO2 is a minor gas, 380 parts per million, which is out of date, because that was the number when I first gave this talk. And the fact that it's out of date is what's so startling and alarming here, that now you could literally update this number year by year, and now that it's over 410, and that it's a tiny number compared to the amount on Venus and Mars, but the fact that it's increased by such a dramatic percentage in such a short period of time is crazy. And and then we'll talk about why that's important climatically. And then the other thing to really notice here is that surface pressure, that Venus is almost 100 times Earth's, and that Mars is slightly less than 1% of Earth's. And consequently, then look at these surface temperatures, and we'll talk about why those have the numbers that they have. But you see quite the dispersion. And in the subject of that scary increase of CO2, I'll probably show the Keeling curve, talk a little bit about that, and maybe mention in passing the sort of seasonal squiggle, which shows the breathing of Earth, the difference in vegetation in the northern and southern hemispheres, basically is why that goes up and down with the seasons. And then I'll show something like this, where you talk about the magnitude of the greenhouse effect, and how, first of all, you see Earth has about 17 degrees of greenhouse effect. This arrow shows where it would be without that. And depending on how much time we have, I might talk about the troposphere and the stratosphere, or maybe not. But at any rate, I show this comparison. And then by contrast, Venus, because it has that massive atmosphere, 100 times the density of Earth's, has this huge greenhouse effect. This arrow shows Venus without the greenhouse effect. When I say without the greenhouse effect, it's the equilibrium temperature, what it would be if it was just that sphere in space around the sun, determined by that equation of thermal physics I showed you. Just the equilibrium without an atmosphere would be where this arrow is. And so all this warming of Venus is due to that massive envelope of mostly carbon dioxide. And then interesting, Mars, you see the difference between the surface of Mars, the surface temperature, and Mars without a greenhouse effect is tiny. Mars has a very small greenhouse effect, even though its atmosphere is mostly CO2, because it doesn't have much of an atmosphere. It's just, again, about 1% the mass of Earth's atmosphere, or rather, the pressure at the surface, not the, well, anyways, is a better way to say it. And so even though it's mostly CO2, it doesn't have much of an effect. Now we'll come back to these, but that's just sort of the lay of the land of the sort of comparative climate of these bodies. And then you can ask, so why are these atmospheres so different? Here are these three rocky worlds so near each other in the solar system. What happened to them so that they arrived at these very different conditions? And some answers in a nutshell, which then I will unpack with more slides, but are the big variables are the planetary size, the position relative to the sun, and then it turns out life is important too. If you wanted to say the one thing about Earth that made it such a freak in the solar system, so different from the other planets, it's the influence of life. You know, we always talk about how Earth is such an unusual planet, and therefore it has life because it has these conditions. It's in the habitable zone, and therefore it has life. But it's equally, maybe even more true to say that because Earth has life, it's an unusual planet. Life has profoundly changed, not just the atmosphere, but the geology, the surface rocks, the mineralogy, even the interior composition and structure of the Earth in many ways is the result of billions of years of life affecting it. So certainly the atmospheric composition, that oxygen, and then a lot of other qualities that come out of that have to do with life. The size, of course, is important as well, because the longevity of Earth's oceans and the longevity of geological activity both have to do ultimately with the size. Earth is a large enough planet so that it's held onto its internal heat, which has kept it geologically active and maintained plate tectonics and so forth. There are a number of levels at which one can go into any of these topics depending on how much time you have and what audience you're speaking with. But I think the basics of discussing these differences between the planets is helpful. With Mars, the one variable that really determines why it's so different is its size. It's true that it's farther from the sun and so it's colder, but the fact that it's small compared to Earth and Venus is what has allowed its atmosphere to be lost over the years, simply because it has much lower escape gravity. And so every single atmospheric loss process, whether it's impact erosion, things smashing into Mars and knocking off atmosphere, or just the other thermal, what we call thermal and non-thermal atmospheric loss, interactions with the solar wind, knocking atoms off the top of the atmosphere, all of these things, all the different ways that planets lose atmospheres, Mars is much more vulnerable to because its escape velocity is lower. So you don't have to, a molecule, atoms don't have to, and ions don't have to be moving as fast. So any process is much more efficient at ridding it of atmosphere. Whether or not the magnetic field of Mars is important in its history of atmospheric loss, that's something that's been actually more subject to debate recently. You'll read in a lot of textbooks or hear people say it's because Mars doesn't have a magnetic field and that's why it's lost its atmosphere. Well, we don't really know that anymore. We used to know it. We don't know it anymore. That happens a lot in planetary science. Things that we know, we don't know later. But it's a little more complicated than that. But to the extent that it has to do with magnetic field, that also is a victim of Mars having a small size, because it's the fact that Mars doesn't have active geology, and its crust and most of its mantle are solid, because it's cooled off. Smaller planets cool off more easily. That is probably also what it does. Probably doesn't have a large convecting core like Earth does, and therefore its lack of magnetic field is also related to its size. And certainly its lack of what I say here, volatile recycling. That's a little nerdy, but that just basically means volcanic activity squirting gases into the atmosphere. In other words, Mars doesn't maintain its atmosphere the way Earth and probably Venus do because of ongoing geological activity, which is again related to size. A small planet cools off and freezes up and doesn't keep up with the volcanism and so forth. And then Venus, the variable that makes it so different, probably above all else, is position in the solar system. Just because obviously it's, if I didn't say this when I showed that first slide with all the numbers, I should have, but another remarkable thing about Venus compared to Earth is that it's almost exactly the same size. The two really are practically twins. Venus is slightly smaller than Earth. And if Earth was a regulation basketball, Venus is a regulation soccer ball. It's a little bit littler, but we don't know of any other pair of planets, I think, in any solar system yet, in any planetary system, which are as similar in size as Earth and Venus. And it's remarkable that the planet next door is so Earth-like in terms of its bulk properties. So why did it end up so different? Well, the basic fact is that its position relative to the sun, it's about, roughly speaking, if this is Earth, Venus, if you go about 1/3 closer to the sun, you get, if this is Earth sun distance, you go about 1/3 closer to the sun. Venus is 2/3 of the way out, but that means that it gets twice as much sunlight because of the inverse square law. So Venus gets about twice as much sunlight, and that's almost surely in some maybe slightly convoluted fashion what did in the perhaps once Earth-like climate of Venus. And also, to some unknown degree, we're learning that its geological history is different from Earth's, and that probably is part of the climate story in ways that we're still sort of unraveling. And now, at this point, I say a little bit more about the history of these worlds, and I talk about the fact that the sun has evolved. And this is something, the HR diagram, I don't need to spend a lot of time on because I feel like probably most of you know more about stellar evolution than I do, but it's a good place to introduce and talk about where the sun fits in, and the fact that the sun also has a biography and is different now from when it was young, and will be different again when it's older, and how the planets are evolving their climates in an environment determined by the slow but inexorable evolution of the sun. And then, out of that understanding of stellar evolution comes a understanding of the way that the sun's brightness has changed. And, again, depending on audience and time, I might say something a little bit more about why that is. And again, I don't have to tell you guys. I'm afraid if I say it, then I'll just say something wrong, and you'll say, actually, that's not quite right. But, hydrogen burning into helium and changing the density of the solar core, and that affecting the balance of radiation and yada, yada. You know this better than I do. But anyways, the point is, You can quote me on that, yada, yada. No, that the point being that it's fairly well established that when the Earth was young and all the other planets were young and first establishing their climates, solar luminosity was something like 30% lower than it is now. And that leads us to a sort of puzzle about Earth that's been called the faint young sun paradox. It may or may not really be a paradox, but it's a faint young sun problem. And that is that because we know the young sun was much cooler and there was much less radiation coming from the sun when it was young, we can calculate the surface temperature of the Earth. And all things being equal, Earth should have been frozen over for much of its early history. When I say all things being equal, if the greenhouse effect was more or less the same as it is now, and this chart here, you can see this dashed curve going slowly rising on the bottom. That's equilibrium temperature of the Earth over time with the slowly rising sun, which is represented by the solid line, the slowly rising brightness of the sun. And then this T sub S is the surface temperature of the Earth. And the greenhouse effect gets a little bit larger. This wedge gets a little larger. That's because you're allowing for the fact you're letting water equilibrate. When it gets warmer, more water goes into the atmosphere, and that makes the greenhouse effect a little larger. But even allowing for that, you see there's a problem that through much of Earth's history, the surface temperature should have been below the freezing point of water. But we know it wasn't, because we have good geological and to some extent biological evidence from earlier than 2 billion years ago, going back to close to 4 billion years, that we know there was we have evidence of sedimentary rocks and various other clues that there was a hydrological cycle on the Earth much earlier than this would imply. So that's what they mean by the faint young sun paradox. Oh, and by the way, I put in this here, you might notice Casting and Grinspoon here. This was actually a review that I was co-author on with Jim Casting when I was a grad student. And this was actually my first ever publication that had anything to do with Earth, not just other planets. And so I saw that and I left it in there because I sometimes forget that I've also studied Earth, but I guess I have a little bit. But anyways, so what's the solution here? Something must have been different. And in some way or another, the greenhouse effect must have been stronger deep in the past. So the Earth's atmosphere must have evolved. So what was it? And this is still a subject of, we don't know exactly. Probably it had to do with the fact that there was almost surely a lot more CO2 in Earth's early atmosphere, which makes sense if you look at the neighbor planets. That's maybe the norm if for the rocky planets in these parts, is that you have a CO2 rich atmosphere, but that the CO2 alone can't necessarily do it. And so there's other ideas. Maybe there was a methane greenhouse early on, maybe biology even played a role in that. Maybe it had to do with the fact that this is a one-dimensional calculation here. And when you include 3D and you include continents and ocean circulation, it gets much more complicated. And people have come up with solutions that sort of work using dynamics and changing the albedo and so forth. But this is still a sort of semi-unsolved problem, or I would say there's more than one way to solve it that we've come up with, but we don't know which one is right. There are ways in which people have said that the early Earth is an exoplanet. And there's ways in which that's sort of true as far as our knowledge. We have these models, we have data that's okay, and we have more than one way to explain things, but we're not exactly sure what is the right one. But this is a good an entree point into talking about feedbacks, which are very important for understanding comparative planetary climate, but then also very important for just generally talking about climate change on Earth as well. And you can talk about positive and negative feedbacks, and how positive feedbacks are destabilizing and negative feedbacks are stabilizing. And very important and easy to describe positive feedback is water vapor feedback. A planet gets a little warmer, and that everybody knows that when a body of water is hot, it'll evaporate. You leave a glass of water out in the sun and it'll slowly go away. And water vapor itself is a greenhouse gas. And so that then heats things up further. And if that's the only thing going on in your system and there's nothing sort of pushing back, then that's a positive feedback that's very destabilizing. And in fact, it could destabilizing. In fact, it can run away. We'll talk about that in the context of Venus in a minute. But the point is that there a positive feedback as seen in this diagram are when you have two different parts of the system that are both reinforcing each other and pushing each other along. And that's very unstable. You start at any point and it pushes off of that point to a state that's very different. Another important positive feedback is ice albedo feedback, where if you have a planet that's somewhat ice covered and you cool it down for whatever reason, that will increase the amount of the planet that's ice covered, and that therefore lowers the planetary albedo. I'm sorry, that raises the planetary albedo. It reflects more if it's more ice covered, and that leads to cooling, which then will increase the ice cover. And again, if that's the only thing going on, it's unstable. That can run away and you can end up with a fully ice covered planet. And we believe that that has probably happened a couple times in Earth's history. So positive feedbacks are destabilizing. There are also negative feedbacks, and I'll talk about a couple of them. One really obvious one, so obvious that in fact, we often neglect to mention it, but it's an important one, is simply the fact that hot surfaces radiate more infrared. Heat something up and it more effectively radiates and cools itself off. And that, it's very simple, but that's a negative feedback, because the hotter you get, the better you are at cooling yourself off, and vice versa. So that tends to be stabilizing. But of course, that can break down if other things are going on. By the way, these last few slides I took from a lecture, a set of slides that's online by Jim Casting. That's really quite good. It's and I can find the link if anybody wants it, although it's easy to find if you just Google Jim Casting faint young sun slides or something. But anyways, I was messing with my slides a little bit this morning, and I changed some of them out because some of Jim's were better than the ones I had, and he had really good set on these different feedbacks. So I stole them from him, but he put them on the web for people to use, so I assume it's okay. Thank you, Jim. So now let's talk about a really important feedback on Earth and presumably on other rocky planets in the galaxy that are habitable. And this is a negative feedback, which is probably the biggest part of the answer. If you go back to, if you go back to this slide, there's the question of what was different about the Earth early on, but there's a sort of secondary question of why has Earth's climate been so stable for so long, given all the external forcings. We know that not the sun has changed, as I've talked about, but we also know there have been a number of different internal forcings where there have been periods of volcanic activity, greater and lesser, and there have been impacts and dust and all kinds of things perturbing Earth's climate. And yet what you see is a record of great stability. Why has Earth's climate been so stable? And we think a lot of it has to do with this feedback loop that we call the carbonate silicate cycle, which actually acts as a climate thermostat. And here's how it works. If you think about the CO2 cycle, volcanoes are always putting out gases, of course, into the air. Carbon dioxide is the most important greenhouse gas. It's not the only one, but it's the most important. And it's always being emitted by volcanoes. And that's the big source. There are also what we call sinks, processes removing CO2 naturally from the atmosphere. And the most important one has to do with rainfall and what we call weathering, that when you have liquid water raining, there's CO2 dissolved in it. And that makes carbonic acid, which is just CO2 dissolved in water. And that running over the land and interacting with silicate rocks basically dissolves those rocks and leads to calcium and carbonate ions in the ocean, which then get redeposited as carbonate rocks. So I said a lot of words, but all that's happening is that the CO2 in rainfall is dissolving and interacting with rocks on land, which then means that the carbon ends up as, here you see calcium carbonate. That's basically carbonate rock. So the carbon gets sucked out of the atmosphere by rainfall and ends up as carbonate rock on the ocean floor. But that's not the end of it. Then over time, because Earth has plate tectonics and the ocean floor gets recycled, those carbonates get subducted or sucked into the interior of the Earth. And when that happens, carbonate rocks, when they're subjected to heat and pressure, they go through what we call a metamorphosis, and the CO2 gets driven off and ends up coming back out of volcanoes. Now that's the long-term natural carbon cycle that humans obviously have nothing to do with. Carbon dioxide comes out of volcanoes, it gets sucked up by rainfall, ends up as carbonates on the ocean, gets pulled into the interior of the Earth, gets broken up by heat, and comes back out as CO2. So that's not a feedback or a thermostat, that's just a cycle. Here's where the thermostat or the feedback comes in. This part of the cycle, the weathering reactions, the rainfall, and the chemical reactions that happen when groundwater is running through rocks, is highly temperature dependent. It depends on the climate. When it's hot, the hydrological cycle speeds up. You have more rainfall and the chemical reactions go faster. And so this weathering is really efficient. So when it's hot, the Earth is really good naturally at sucking CO2 out of the atmosphere. When it's cold, the opposite happens. At its extreme, if the Earth freezes over, then this hydrological cycle, the hydrological cycle stops. There's no rainfall, there's no groundwater because everything's just frozen over, and the CO2, the sink just stops. So when it gets really cold, you stop removing CO2 from the atmosphere. So this part of the cycle, this weathering part, is highly dependent on climate. But this part, the source, the CO2, doesn't care about climate at all, because volcanoes generally, and geologists here might argue with me a little bit, but generally speaking, volcanoes don't care about the climate. They'll just keep putting out CO2 throughout the Earth's entire history. So the source is independent of climate, but the sink is dependent on climate. That leads to a thermostat effect. The hotter the Earth is, it'll start to pull CO2 out of the atmosphere. The colder it is, CO2 will build up in the atmosphere and therefore will push back, CO2 being a greenhouse effect. So that has a powerful long-term thermostat effect on the Earth. Now, this is a good place to interject an answer to a question that may pop into people's heads. The question being, well, wait a minute. So does that mean we don't have to worry about climate change because the Earth fixes CO2 imbalances? And the answer is, sure, if you've got 1 million years to wait, then there's no problem, because that's the time scale in which this operates. It says here 500,000, 1 million. But the point is, much longer time scales, the Earth will eventually correct any carbon imbalance. And this is why when people say, the climate change is permanent, I think, well, it's not really permanent, but it's much, we don't have time to see that change. So there is a long-term thermostat effect, which is very important in the evolution of Earth's climate, but doesn't help us at all with our immediate problems. Now, going back to comparative climatology, these same processes, we believe, we believe that this same climate thermostat probably at one point operated on both Venus and Mars, because we see evidence that both Venus and Mars had surface water when they were young. At least we see good evidence on Mars, and we have circumstantial evidence on Venus that we're hoping to solidify with our missions this coming decade. But what happened? We think that on all three planets, this thermostat operated early on, but then it broke on Venus and Mars. And it broke in different ways on both those worlds. On Venus, the water was lost. I'll talk about that more in a minute. But basically, once you've lost your water, then this part of the cycle, the weathering, stops. It's dependent on water. That reduction of CO2 in reacting with rocks doesn't work if the system is dry. But the volcanoes keep going. So then all the volcanic CO2 ends up in the atmosphere. There's no way to remove it. And your system just ends up pegged in the red zone, hot, with no way to cool off. And you've lost all your water, and you just have a CO2 rich atmosphere. On Mars, it was the opposite problem. This part of the thermostat broke. The volcanism died out early. Mars, being a small planet, lost its internal heat, lost most of its internally generated geological activity, and therefore you had no longer had a CO2 source. And over time, most of the atmosphere has been lost into space. So this is just a schematic drawing of that same carbonate silicate cycle that I was talking about. If you like schematics better, but it's the same thing we've already been discussing. So on Earth, today, here's the basics of the greenhouse effect. The solar flux and the albedo combined give us the equilibrium temperature. And then the greenhouse effect gives a surface temperature, which is the equilibrium temperature plus this delta T for greenhouse. And the greenhouse, as I described, has these really radically different values for Earth, Venus, and Mars for reasons we've been discussing. And by the way, this is kind of a nifty chart too. The Earth's current greenhouse is 25% due to roughly CO2, 15% due to a series of other gases, and about 60% due to water, which people will see this and they'll go, oh, wait a minute. So water's the big culprit, not CO2 or methane. But the thing is, water is a passive responder to climate on Earth. It's true that it's a major greenhouse gas, but because Earth is a water planet, we don't have any control over how much water there is. Water will respond to and amplify anything else that's changing the climate. And there's really little that can be done about that. So it's a major greenhouse gas, but it's not a forcing that responds at all to things that we do. And yeah, this is just a summary of those different feedbacks. And then one more episode of Earth evolution that's interesting to mention, and also sort of another illustration of climate feedbacks, is that at times Earth has been completely frozen over. I said Earth has been remarkably stable in its climate, and that's true, but there have been a few dramatic excursions from that in Earth's long history. And there have been a couple times when Earth has been basically completely frozen over, and we call these snowball Earth episodes. And the biggest and most serious of these happened about 2.1 billion years ago. We call this the Paleoproterozoic snowball Earth episode, which is just because that's when it happened, was in the beginning of the Proterozoic, so Paleoproterozoic. And it coincides with the rise of oxygen on Earth. And the rise of oxygen on Earth has to do, of course, with the evolution of life, and life learning to tap into sunlight and perfecting photosynthesis, using carbon dioxide and water to make food, carbohydrates, and liberate oxygen. And when that happened, eventually oxygen shot up in Earth's atmosphere. And we believe it's not a coincidence that that coincides with this global glaciation. We think that that all that rise of oxygen not only caused a mass extinction, because the organisms that were around at that time couldn't handle all that oxygen chemically, but it also probably crashed the climate. And the way that happened, we think, and we're not totally sure about this, is that at that time, the Earth was being kept warm partly by a CH4, by a methane greenhouse. And due to the evolution of the cyanobacteria, which were the organisms that did all that photosynthesizing and released all that oxygen, then the oxygen built up in the atmosphere, and oxygen rapidly destroys methane. So if Earth was being warmed at that time by a methane greenhouse, then the release of all that oxygen would have destroyed methane easily, and that would have crashed the climate, leading to an ice runaway. And as I mentioned before, that's a positive feedback where you start to ice over a planet, and that cools it off because it raises the albedo, reflects more sunlight, and that can lead to, that can run away, lead to a totally frozen over planet, which we think happened a few times. And so how did we escape? How did Earth escape from that? Well, it had to do with that carbonate silicate cycle that I was talking about, because even though the global glaciation completely shuts down weathering, then there's no sink for CO2, but the volcanic source persists. The volcanoes keep going. So after a while in that frozen over state, the atmospheric CO2 builds up and builds up and builds up, and then the greenhouse increases and it basically melts through the ice. And after maybe 10 million years or so, then Earth returns to, quote, normal, although normal from then on would be a much higher CO2 level than it was before this happened. So this is all just another interesting illustration of the kinds of feedbacks that we think have dominated Earth's climate history. Now, let's see, I don't want to take, I'll go for another, started a little bit late. I'll go for another 10 minutes here, but then I want to make sure we have plenty of time for discussion. I want to talk for a few minutes about Venus now. Comparative climatology of Venus and Earth. And things to point out here are the great similarity in size, diameter, and mass of Earth and Venus. They really are twin planets in important ways, and therefore escape velocity is very similar. But the dramatic difference in surface pressure, I already mentioned, and therefore, and well, partly as a consequence of that, the dramatic difference in surface temperature. And then also fascinating on two planets that are so similar in so many ways is the huge difference in water abundance. Venus has, Earth has 100,000 times as much water as Venus. And given that the two planets seem to have formed, as far as we can tell, from similar materials, that's a striking difference. And they also have probably fairly similar carbon inventories, although we're not exactly sure what the carbon inventory of Venus is. But the difference in water is really striking. A common assumption we make, and this is something we're going to definitely be testing with the Da Vinci mission coming up later this decade, is that the initial conditions were the same. There's a lot of circumstantial evidence for that, a lot of reasons we believe that, although we don't really know very much about the initial conditions of Venus. And for that matter, as I've mentioned, there's a lot about the initial conditions of Earth we still don't know. But we assume initial conditions were the same, and then that this great difference represents a divergence between the two. So what happened to Venus? In a sort of cartoon sense, we think we know the answer. Venus was born too close to the sun compared to Earth. If they were born identical, but then Venus was that much closer to the sun with twice the solar radiation, then you would have had a powerful runaway greenhouse with a powerful positive feedback. Of course, I used Jimi Hendrix to represent feedback. But as I already described, this water feedback, if you have a higher surface temperature, you get more water vapor in the atmosphere, greater infrared opacity, and all other things being equal, it can run away. You get a steam atmosphere, the hydrogen escapes to space, and the result is that today Venus has only 1/100,000th of Earth's amount of water. Now that's our cartoon understanding, but we want to do better and see if that's really true and try to get information and ask, well, is that really what happened? And when did it happen? And what are the details? Now, by the way, I'm just going to tangentially mention something that I learned in giving this talk, because when I first gave this talk, I used a version of this slide, but I didn't say born too close to the sun. I said Venus, the problem is Venus was born on the wrong side of the tracks. And I used train tracks here for the inner edge of the habitable zone. But I gave that talk a few times. And then somebody came up to me after the talk and said, you know, that phrase, born on the wrong side of the tracks, you should be aware that that can be seen as racist. And at the time when somebody told me that, I was really taken aback. I said, what are you talking about? You know, I'm not racist. And that's not what I mean. As far as I knew, that was just an expression meaning, you know, born in the wrong place or whatever. So I kind of, internally, at least, I mean, I was polite in the conversation, but internally I was very defensive and thought that's ridiculous. You know, that's a ridiculous thing to say. But I thought about it after that. And I read up, you know, I Googled the phrase and how people were using it. And I realized that this person was right, that I did not want to say Venus was born on the wrong side of the tracks, because that is an expression that in some places has meant something racial. So I stopped using that and I changed the slide to born too close to the sun. So there you have it. Sometimes when somebody calls you out on something, you can react. Your first initial react can be defensive because it's like, well, that's ridiculous. That's not what I meant. But then I think in this case, the criticism was correct. So I figured that out and I changed the slide. Anyways, moving right along. So that's sort of the cartoon version of Venus. As we've studied Venus with missions and more observations and models, we've discovered that it's actually a very complex place. And there are some really interesting climate feedbacks going on Venus, because we believe, although again, almost all these things I'm saying we believe about Venus are things we want to test out with our upcoming missions, but we believe there is ongoing volcanism. And that means there are volcanic gases like water and SO2 that are being actively supplied to the planet. And those gases, it turns out, are important in the clouds, making sulfuric acid, which supplies the clouds, is probably a product of these volcanic gases interacting with ultraviolet sunlight, which means that if the volcanoes ever stop for 10 million years or 100 million years, the clouds probably go away on Venus, which really changes the climate balance. So by the way, if you go out and look at Venus tomorrow morning, it's up in the morning right now, it's beautiful. It's easier for me to see it when it's in the evening because I'm not a morning person like sushi. No. But good morning. When you see Venus with your naked eye, it's so bright and beautiful. You are seeing, I believe, naked eye evidence of ongoing volcanism on Venus. Because I think the reason why Venus is so reflective, the most reflective planet in our solar system, is because of that thick, constant cloud cover, which I think, if our models are correct, is a result of ongoing volcanism. So you can, with your naked eye, see evidence of ongoing volcanoes on Venus. But the result of that, the point here is that the climate, it turns out, is very complex because you have gases actively forming the clouds, which are hugely important in the climate, changing the surface temperature, and the surface temperature also changes the kinetics and the equilibrium point of these surface atmosphere reactions between gases and minerals. So Venus, it turns out, has a very complex climate with all kinds of feedbacks that probably rivals the complexity of Earth's climate system, even though it doesn't currently have a hydrological cycle. The sulfur cycle on Venus is very complicated, and we're just starting to understand it. And it seems to be probably mediated by active volcanism and sunlight, ultraviolet light. And so it may rival the complexity of Earth's climate. So we're still trying to figure it out. And my colleagues and I, we call this Venus system science. And as far as my own research, I've done more along the lines of this than anything else, of really trying to understand the interactions of all these different reservoirs, the interior surface and atmosphere, and the fluxes going between them, as well as external forcing and how that affects the climate of Venus. And one result that we've had recently really changes the way that we think about Venus in kind of a neat way. This is a paper that we published in GRL a couple of years ago. And Mike Way was the first author. He's at Goddard Institute in New York, and gave it the provocative title was Venus, the first habitable world of our solar system. And this paper was a result of our applying a Earth GCM, general circulation model, the kind of models we use to predict climate change on Earth, getting it to run for Venus, which is not as easy as it sounds. It should be easy, right? Because if these climate models are good, they should just be using general physics, which you can apply to any planet. But the actual tweaking it to run on another planet is harder than you would think. And we discovered a lot of things that were tuned to Earth that they shouldn't be. So you learn things about these models that help you do a better job on Earth when you do an exercise like this. But we got it working really well for Venus, and we discovered some things that surprised us. And the main one was, we think we can make a good case for oceans on Venus having lasted much longer than anybody thought. We used to think that if there were oceans on Venus, you probably had a runaway greenhouse effect very early in the planet's history as the sun started to heat up. But those models did not include clouds. It's very hard to include clouds in evolutionary climate models. They're really the hardest thing to model for reasons we could get into. But when you include a full up general circulation model for Venus and you include the role of clouds, you get a very different result, because and this only works for a slow rotating planet like Venus, but it turns out that with clouds, the planet organizes itself, the atmosphere and the clouds organize themselves in such a way as to maximally keep the planet cool for billions of years longer than we thought. Because if you have a slow rotating planet and you model the circulation and you model the clouds, you end up with a planet where the sunward facing side of Venus, or whatever planet this is permanently cloudy, completely clouded over. And the anti-sunward side, the night side, is completely clear. And that's a perfect combination to keep the planet cool, because the cloudy sunward side acts as basically a big reflector, cooling the planet. But if you have clear skies on the night side, just as when it's clear on a cold night where you are on Earth, it gets colder because you can radiate to space much more efficiently without clouds getting in the way. The planet radiates much better, much more easily, much more efficiently on the night side without clouds. So if the clouds end up in that configuration, and apparently they do if the planet is rotating slowly enough, like Venus is, then you can stabilize surface oceans for billions of years. So this has a couple of very interesting implications, which I'll mention briefly. One is that you might have to think of the habitable zone, that is the classic habitable zone of liquid water on planetary surfaces at a certain distance from a star, as being dependent on the planet's rotation rate. Because what we found is that if Venus had an Earth-like rotation rate, this wouldn't happen and it would have lost its oceans much more quickly. But it's the slow rotation rate that leads to this organization of the clouds. So the inner edge of a habitable zone may be highly dependent on rotation rate of a rocky planet. Another amazing implication is to think about what this means if Venus really did have oceans for over 2 billion years, which we now think is quite possible. Think about what was happening on Earth during all that time. And it may be that through much of our solar system's history, there were two planets right next door to each other, rocky with surface water oceans, maybe even exchanging material, maybe even exchanging life. So that's kind of a mind-blowing thought. Let me very quickly say a few things about Mars and Titan. I am going to do this quickly because I don't want to just blow through all the time, and I've been kind of rambling. So very briefly, we have all kinds of evidence for water on Mars. You've heard about it, so I'm not even going to really summarize it here. Layered terrain, surface minerals discovered by the rovers that were formed in the presence of water, meandering riverbeds, what seem like ancient shorelines. You've heard it all. So Mars was warmer and wetter, but what was different? Again, the carbonate silicate cycle may have obtained early on in Mars, but broke because Mars was too small, the volcanoes died, and with low gravity and escape velocity, the atmosphere was lost. So that's how we sort of understand why Mars is the way today it is today. But if you try to back it up in time and say, okay, so it had a lot more atmosphere, therefore it was warm and wet, it doesn't quite work. At Mars's distance from the sun, it's hard to make it warm and wet. You think, well, you need a strong greenhouse. So of course you just add a lot of CO2, right? And that would work. The problem is it doesn't work. CO2 greenhouses at Mars's distance are self-limiting. The clouds start to warm themselves, then they dissipate, and you basically can't get the surface above freezing just using CO2 at Mars's distance because of the behavior of CO2 clouds. So what is it? There are several alternatives. I'm just going to list them now and then move on. We could come back to this in the discussion if you want, but basically it could have been just occasionally warm and wet through impacts and never warm and wet in an equilibrium state. And that could have actually over time left the geological evidence. And more recently, people have suggested there could have been a very thick hydrogen atmosphere. And hydrogen, you don't think of as a greenhouse gas, but hydrogen in combination with nitrogen or with CO2 leads to these collisional modes where you sort of are briefly altering the dipole of hydrogen in such a way that it gets asymmetrical and can absorb infrared. Good luck telling a popular audience about that. But no, I mean, you can talk about just, we've learned recently with newer modeling people have done that, in fact, a thick hydrogen envelope in concert with other gases can have a greenhouse effect that we didn't really realize before. There's even the idea that maybe if there was abundant early life on Mars, that it could have produced a methane greenhouse and had sort of a Gaia type effect on early Mars, where life itself kept the planet habitable for some time. Okay, the last thing I want to mention, because I think it's relevant and interesting in this discussion, is something about Titan. I won't go into much detail, but you all know about Titan, moon of Saturn, with some interesting similarities to Earth. They both have mostly nitrogen atmospheres. They both have high surface pressure. Titan actually has a higher surface pressure than Earth. It's the only moon with a thick atmosphere, and it's even thicker than Earth's. It has, like Earth, it has a major constituent in three phases. Where Earth, that's water. On Titan, it's methane. There's liquid and gaseous methane on Titan. And so you have a liquid cycle with clouds, rain, and lakes, only it's not water on Titan, it's methane. And then there's some important differences as well. Obviously, it's much colder. Earth is much larger, et cetera, et cetera. But the interesting parallel that's worth mentioning in a comparative climate talk is that Titan has a lot of mechanisms, climate mechanisms are similar to Earth. Methane is the key to maintaining its warm temperature. There's a methane greenhouse, which, 94 Kelvin may not sound warm to you. It doesn't to me either. But without that methane greenhouse, Titan would be so cold that the nitrogen would freeze out and it wouldn't have its thick nitrogen atmosphere. It's the methane acting like water acts on Earth. That is that trace greenhouse gas that keeps the planet warm enough. So without the methane, the atmosphere and climate of Titan might completely collapse. Yet, interestingly, methane is destroyed on a short time scale and must be replenished somehow. I don't think I'm going to talk about that now, though it's an interesting story. But the way that methane is destroyed in the atmosphere has other climate implications. Basically, there's all this photochemistry going on because of photons, ultraviolet photons from the sun, but also to some extent because of high energy electrons in Saturn's magnetosphere that are blasting into the methane in the upper atmosphere and knocking off hydrogens And then you have these CH3 ions, which are unstable and want to find each other, and they find each other and make things like ethane and acetylene, and the hydrogens keep getting knocked off, and the ions find each other and make more and more complex organics. So Titan, with all this methane and with all this activity in the upper atmosphere, stripping off hydrogens, making heavier organics, you end up, oh, and there's also nitrogen, which gets split up by the electrons from Saturn's magnetosphere, and then you'll get nitrogen-containing organics like cyanide and other things, which is really interesting from a biology point of view, a prebiotic chemistry point of view. But also you end up with this thick haze in the upper atmosphere of Titan. And this is actually a Voyager image showing this beautiful upper atmospheric haze. That's why, by the way, you cannot see the surface of Titan from space in the visible or with a telescope. It's all covered with this haze. You can see in the infrared or with radar, just like Venus, but not in the visible. But that haze has a really interesting climate effect. It leads to an anti-greenhouse effect that's actually pretty strong. The anti-greenhouse effect is just like it sounds. So as with the greenhouse effect, as we discussed, is when you have incoming visible radiation that makes its way through, but the outgoing thermal radiation is blocked. Well, and that warms the surface. The anti-greenhouse effect, if you have aerosols of the right size distribution, it does the opposite. It lets infrared through, but blocks visible. A lot of aerosol hazes will do that. And the net effect then is to cool the surface. And so in fact, on Titan, the greenhouse effect would be much greater without this anti-greenhouse effect. And this is interesting to talk about because it also leads back to some important phenomena on Earth. When you have a volcanic eruption and it puts aerosols into the stratosphere, like Mount Pinatubo did, and it cools the Earth for a few years, that's the anti-greenhouse effect. It's the exact same physics as what's happening on Titan with this upper atmospheric haze. It's also, by the way, the same as a nuclear winter on Earth, something which is bizarrely and strangely and frighteningly become more relevant to discuss again now than it seemed for many years. But that's how a nuclear winter works, is by putting aerosols into the upper atmosphere and having an anti-greenhouse effect where you're letting through infrared but blocking the visible, and you're therefore cooling off the troposphere of a planet if this is happening in the stratosphere. I'm not going to go into any more detail about this now because I want to wrap up and have discussion, but there's a wonderful paper about this that was where they lay it out really well. It's really well written and understandable. Highly recommended. It was in Science in October 91 by Chris McKay, Jim Pollack, and Regis Cortan, the greenhouse and anti-greenhouse effects on Titan. And they starts off, as you can see, the beginning of the abstract, talking about many parallels between the thermal structure of Titan and Earth's greenhouse effect. It's just, if you want to get into this, I recommend this paper. It's really nicely written. I think I want to wrap up. I was going to say something about dust storms on Mars, and I'll just say it really quick. The difference between a clear atmosphere and a dusty atmosphere on Mars, you see these two dotted lines here, is dramatic. And it's the same thing. It's basically a kind of an anti-greenhouse effect where when Mars gets dusty in the atmosphere, the radiation's being absorbed in the upper atmosphere rather than at the surface. And so the same amount of heating is going on in the atmosphere, but it's not going on at the surface. And therefore you have a lower surface temperature when the atmosphere gets very dusty. And this, by the way, this work was done by the same people using the same physics who came up with the theory of nuclear winter on Earth. They looked at this happening on Mars and they said, oh, well, what happens when all this stuff gets sent up into Earth's stratosphere? And they did the calculations, and you can look at the authors are the same for these Mars papers and for the nuclear winter papers on Earth using the same physics. So anyways, really quickly, some conclusions. Planetary climate is complex and uncertain, but other planets do show us that our climate models work. If we're worried that, what if we're really missing something? Well, we should be able to predict the surface temperature of Mars, of Venus, of Titan based on physical principles that we apply to Earth. And it basically does work. There's a lot of details we haven't worked out. But to first order using the same physics, we can say, given this atmosphere and this much radiation from the sun, the surface temperature of Mars should be this, and it is that. So we have this sort of basic validation that our climate models work. And radical change of climate does happen in planetary history. Earth has been remarkably stable, but that's no guarantee of future performance. Even fatal climate change has happened before. What is new here on Earth is premeditated climate change. Now that we understand all this, we can see it coming. And so that gives us a certain responsibility. And we need all the help we can get, including data from other planets to help us see what we're missing, to validate our models. Earth is, of course, unique, but planetary observations and modeling give us a reality check on our assumptions about climate modeling and provide indispensable perspective on the uniqueness, the deep past, and long-term fate of Earth. And so, of course, there's a lot more to say, but I'm going to stop because it's about time to hear what you guys have to say and to engage in some conversation. So sorry I went on so long, but thank you.
Thank you so much, David. That was really informative. I have a few questions, but I want to give the audience a chance to maybe start us off. So if you have questions, feel free to unmute or type it in the chat and I will read it out for you.
Yeah, I have a question, if I may. So you mentioned Mars losing most of its atmosphere over its history because it's small, it has a weak gravitational field. But Titan, for some reason, kept its atmosphere while it's smaller than Mars. How come?
Yeah, great question. There are a few parts of that. I mean, you can back up and ask, why does Titan have an atmosphere in the first place? If you look at the other similar moons, like Ganymede is the same size as Titan, basically, and Callisto, moons of Jupiter, but they don't have an atmosphere, right? So that's rather odd. That's rather odd. We think that Titan has an atmosphere, and Ganymede and Callisto don't, because for a couple of reasons. One is the Saturn system is in its formation was different from the Jupiter system because one is that it's colder out there, so the dominant gases, the dominant volatiles are going to be different and less. The energy from the sun is just less, and so there's less energy leading to heating and an atmosphere and causing it to escape. But also, when those planets were forming, the impact environment was very different, and impacts and a forming atmosphere have these paradoxical effects where on especially icy objects in the outer solar system, they can bring in material. Think of a comet hitting primordial Titan or primordial Ganymede. It can add icy material, which may end up in the atmosphere, right, if it melts and vaporizes, but it can also blow stuff off. So it's the high velocity impacts remove atmosphere from a young icy moon, and the low velocity impacts add atmosphere to a young icy moon. And it turns out that if you model the velocities of impacts in the Jupiter system when it's forming compared to the Saturn system, that can explain the difference, because Jupiter, both because it's closer to the sun and because Jupiter is so much more massive than Saturn, the average velocity of impacts hitting Ganymede and Callisto was much higher than the average velocity of impacts hitting Titan. And so the average impact on Titan led to accreting atmosphere, whereas the average impact on Ganymede and Callisto led to eroding atmosphere. So that's how Titan started off with an atmosphere. But that doesn't really fully address your question. How did it keep it when it's so much smaller than Mars? I think there's a few differences. One is, of course, Mars is much closer to the sun, and a lot of the processes stripping atmosphere off have to do with the solar wind and just solar radiation. So things are more quiescent and more stable out where Saturn is. But I think it's also the primary volatiles. Well, no, that's not true, because Mars, CO2 and yeah, it's interesting because on Titan, you can consistently replenish the atmosphere because the atmosphere and the surface materials are the same materials, right? So if you lose some atmosphere, as long as you have a warm enough surface, kept warm by that methane nitrogen greenhouse, then you're just going to keep evaporating surface material to reach that equilibrium. That the thickness at the surface of Titan is determined by the vapor pressure of the methane and the nitrogen in contact with the surface, right? So, I mean, I suppose if you lost enough atmosphere, then you would ultimately lose the entire planet because you're losing the same material that forms the solid planet, but you're just not losing it at that rate. But I think it's more a question of the fact that on Titan, the entire surface of the planet is made out of the volatiles that are the same material in the atmosphere. You know, you have nitrogen and nitrogen rich and organic rich material, and you have water ice, all of which one way or another end up in the atmosphere. Whereas Mars is, you know, is rock. And so it's not just, there's nothing on Mars really replenishing the atmosphere. Whereas on Titan, there are sources from the surface. That was a convoluted answer, but I think I arrived at it eventually.
Yeah, thank you.
I will go ahead and ask. I actually have a question about geoengineering and if your climate models have you seen stuff about using the current climate models to look at potential like geoengineering impacts? And I know that when we have discussed it in like my engineering classes, there would be like unforeseeable like agriculture or health effects and stuff. So I was wondering if you could kind of speak to that.
Absolutely, yeah. So when we talk about geoengineering, I mean, of course, there's a lot of different kinds of geoengineering people have talked about, but the sort of classical kind, and I think the kind that maybe you're thinking of, is injecting stuff in the stratosphere to cool the surface. And actually, it's interesting because the physics of that are exactly the same as the anti-greenhouse effect that I was talking about on Titan, or a nuclear winter, or the Mount Pinatubo, you know, the volcanic injection of SO2 on Earth. You're basically talking about mimicking that by injecting SO2 into the upper atmosphere. So yeah, these planetary analogs can help you to understand and explain what that's all about. The other takeaway, though, that I have, I guess, from all of this is that there's so much about climate that we still don't know. And these considerations I've been talking about are basically one-dimensional, where, okay, you have a certain amount of radiation coming in, and then you have a certain amount of infrared radiation being re-radiated and retained, and that's what heats up the lower atmosphere. And then if you have a haze up higher, either because of a volcano or organic haze in the case of Titan, or geoengineering, and if you're doing it on purpose, then that is going to be absorbing some of the radiation and reflecting it back into space, re-radiating it back into space high in the stratosphere, so that there's less radiation to come in and act on that greenhouse lower. But that's a one-dimensional consideration, and it works. It's like, oh, great, that would work. That would cool the Earth. No problem. Why don't we do that? The problem is the system is much more complex than that. We don't live on a one-dimensional planet. And when you try to model the effects of what that would do if you actually use a three-dimensional GCM and include all the detailed physics and what's happening with ocean circulation and the hydrological cycle and the winds and the clouds, you realize two things. One is that the effects are going to be very different in different parts of the Earth. It's not just going to be, oh, the whole Earth just gets a little bit cooler. Wouldn't that be nice? It's going to be, there's going to be places that get much cooler, places that don't get as cool, and that the circulation is going to be altered. And so we don't really know what it would do, say, to the monsoon in India, or to rainfall in the Nile Delta in Africa. And these phenomena that millions of people's lives depend upon for agriculture and so forth would be affected in ways that we just can't predict. So one realization is that it's non-uniform around the earth. The other realization is that our science isn't good enough to predict the results in detail at every locale. So the more you learn about climate modeling, I think the more cautious you are about quick fix ideas like that. In fact, I would say the people I know who know the most about terrestrial climate modeling, people that know a lot more than I do about it, are the people that are most wary of this kind of geoengineering fix, because they know how much we don't know. And that's in addition to these other problems of moral hazard and continuity. Okay, if we can do that, are people going to say, well, then we shouldn't worry about emissions? Or are we going to get dependent on a system like that? And then what happens if we don't have the continuity of government or whatever to maintain it, then and we stop doing it, is then are things going to bounce back in the other way? There's all kinds of ways that it's fraught beyond just the science. But even with just the science of it, I feel as though it's an interesting thing to contemplate, that maybe someday we'll know enough to want to do that. But I think that it's a bad idea to sort of focus our ideas about solutions on something like that, because there's so many ways that it could go wrong. And more fundamentally, we need to solve the problem by changing our energy systems and just cutting down our emissions and learning to be less dependent on fossil fuels. That people say, well, maybe that's a last ditch effort later in the century, if if all else fails. But to me, it's just not a good place to focus our energies on. But it is interesting to think in a longer term. If we're talking about how to solve climate change in the 22nd century, the 21st and 22nd century, it doesn't really seem to me like that's going to be the key. It's going to be much more changing our relationship with carbon and changing our energy supplies. In the very long run, if we achieve some kind of a mature scientific society that can really know a lot more about the earth and about how to handle ourselves, maybe at some time in the future, we'll want to manage the climate in interesting ways. And maybe we'll want to even, engineer other planets. And that comes into, it's related to that thought about terraforming and so forth. But to me, that's like something that, we have sort of more immediate tests to get through this current century. And that's not really an obvious part of the solution. I don't know if that helps.
No, that was excellent. Thank you.
I've got a question about sort of the prospects for climate modeling on Earth versus climate modeling on solar system planets versus climate modeling on exoplanets. Can you comment sort of how maybe new frontiers in exoplanet science might be helping us out closer to home?
Yeah, I think there are always unforeseen benefits of kind of looking at a problem on a different scale than you're used to thinking about it. And I think what's great about exoplanets is, all of a sudden we have to really expand the parameter space on which within which we model climate, because, when it was just the planets of the solar system, it was already like, okay, well, we have to be able to handle, a planet with 1/3 Earth's gravity, and we have to be able to handle a planet with 100 times Earth pressure. But there were sort of a few discrete examples of things we needed to model. Now we know that all that parameter space, basically, you name it, it's filled somewhere in terms of all these variables of escape velocity and, just wide range of atmospheric compositions and wide range of stellar radiation spectra and intensities. And so it just sort of forces us to really expand our tools in ways that have got to come back and make us more sophisticated about Earth modeling. I'm trying to think of a specific example. I could think of several specific examples. I already mentioned a few where within the solar system, where we realized things from studying other planets. I mean, the anti-greenhouse effect was one. Chris McKay, looking at the anti-greenhouse effect on Titan, he named the anti-greenhouse effect from studying Titan, and now people talk about it on Earth all the time. And there are a lot of subtleties of things that we, from looking at Venus, we realized that we didn't understand the spectrum of CO2 as much as we thought we did, because you have to look at the far wings of the CO2 bands, which don't seem important on Earth, but when you have 100 bars of CO2, then it's not just the center of the CO2 bands, but these far wings, and we realized we didn't quite know the shape of that. So there's subtleties that we learned about the spectrum of CO2 by looking at Venus that now help us do a better job on Earth. I'm not thinking of a specific example. I'm sure there are some of exoplanet climate modeling feeding back and helping us do better on Earth. But I mean, for example, one thing that I suspect, one thing we're not good at on Earth is modeling clouds. It's the weak point. If you look at those charts that show you the uncertainties in the climate forcings from all the different sources of uncertainty, the biggest ones are clouds, because clouds are hard to model, and depending on the particle size and the altitude and other things, clouds can either can force climate one way or the other way. They can be positive or negative feedback mechanisms. And so I suspect that by increasing our ability to model all this wide range of atmospheres and do it well, we're going to learn things about how to model clouds that will probably feed back and help us do a better job on Earth. I'm sorry I can't be more specific now, but I think that just stretching our sort of conceptual muscles and using our tools in all these new ways, it either breaks them or it makes them stronger.
No, that was really great. Thank you.
Hey, David. So thanks for doing this talk. So I had a question maybe that goes a little bit back to geoengineering perhaps, but you were talking about this idea of the Earth sort of being this thermostat and this very capable system, which kind of has its own gauge of self-resilience in a way. So I was wondering if you have any thoughts, or if there's any current research in engineering which is going on about kind of leveraging this idea of the Earth being this feedback loop of a thermostat and kind of being able to use the Earth in a way to help us in our current drastic situation of really helping our climate situation.
Actually, yeah, that's a good point, because there's another form of climate intervention. I suppose you would call it a form of geoengineering, where people have talked about using there's certain minerals like olivine, where if you expose enough of them, they can actually become active sinks for CO2. So people are talking about about finding ways to create locations where you're exposing a lot of these minerals to sort of, you're basically, if you're doing that, you're enhancing the weathering part of that thermostat. So yeah, definitely the more we understand the natural cycle, the more we can find ways to tweak it. And I don't think it's inherently a bad idea to do that. It's just that we don't want to, doing something like messing with the stratosphere when we don't really fully understand how it works seems ill-advised, but certainly trying to understand that carbon cycle. And yeah, if there are ways that we can speed up weathering. In fact, people have talked about, there's another intervention people have talked about, which is seeding the oceans with iron filings in places, and then therefore increasing the growth of algae, which then therefore increases photosynthesis, which draws down CO2. And people have, of course, criticized that as well and said, well, there's going to be unintended consequences. And I think any sort of large scale intervention in the Earth system, we have to be really careful and start off with small scale experiments and make sure we know what we're doing and we're not producing unintended consequences. But certainly understanding the natural carbon cycle is absolutely key. Understanding it really well if we're going to get to the point where we feel confident enough and comfortable enough sort of trying to intervene. I mean, and if you think of geoengineering writ large, you could argue that anything we do to try to intentionally change the climate of Earth is a form of geoengineering, right? Like even if we're planting forests, that seems pretty benign. But if we're saying, well, we're going to intentionally forest this area that wasn't forested before, or reforest this area to draw down CO2, that's a form of geoengineering, right? We're intentionally changing a part of the Earth so that we can change the atmosphere. So if you look at it on a spectrum like that, then there are more benign forms of geoengineering. And then, somewhere in between, people have talked about these ways to sort of artificially enhance a photosynthesis and make it better, engineer forms of life that do a better job of photosynthesis. And again, you got to be careful. You don't want to create something that gets out in the wild and does all kinds of awful things. But I think there's a spectrum from planting trees to messing with the stratosphere. And along there's all kinds of different levels of intervention, some that seem much more benign than others. And it's worth our while to research the whole system and figure out where we think we can have maximum effect without, doing anything foolish.
Cool, thank you.
I have another one if other people don't. What can you speak to what you think are going to be probably the most important contributions that Da Vinci and Veritas are going to give us in terms of being able to study Venus after so long, and then how that could help us?
Yeah. So I think that with Da Vinci and Veritas, we stand a real excellent chance of narrowing down some of the, really the major questions we have about the evolution of Venus and how it compares to Earth. I told you how these ideas we have about what we think happened with the runaway greenhouse, and we think that because of this happened with the clouds, that there may have been oceans for this long instead of that long, but it's all very conjectural, and there's all, if you're going to talk about it with any, degree of honesty, you have to put in so many caveats of like, but we're assuming this and we don't really know that. The fact is, we know nothing about early Venus. We don't know if there ever was an ocean. We know that, we have reasons to think that there probably was a lot more water at one point, but we don't really know if it ever condensed on the surface. So I think with Da Vinci and Veritas, we'll be able to answer that question. We'll be able to say Venus was an oceanic planet at some point in its past, or it never was. And we'll be able to answer the question of whether Venus really does currently have geological activity, or whether that's just a bunch of circumstantial evidence and we're wrong about that it's not currently active. And we'll be able to, there's a lot of real first order questions. Our knowledge of Venus now is sort of like our knowledge of Mars was in the early 1970s, after we had Mariner 9 and had sort of seen our first global maps, but didn't really have any detailed knowledge. It's much more primitive than our ideas about Mars because it's a harder place to explore. And I think it's really important just to characterize Earth, because it's this nearby place that's a twin of Earth in some ways. And we have these ideas about how to evolve, but I think we'll really fill in those missing pieces and know if Venus was an Earth-like place and what happened to it. And that has so many implications. That has implications for how we understand the future of Earth, because it may be that Earth's future is going to be what happened to Venus, is sort of just delayed because we're farther out from the sun, and those effects sort of sweep outward as solar luminosity slowly increases. And it helps us characterize Earth in terms of the habitability of planets in the galaxy. As we start to see learn more about exoplanets, if we understand the Earth-Venus difference, then I think we'll have much more clarity when we see Earth-like planets, and we'll know if they're really Earth-like or not. And then in terms of these questions we've been discussing about climate, it really helps us narrow down kind of the trajectories of climate evolution on Earth-like planets and what can happen. And that certainly has implications, as I said, for long-term evolution of Earth, but I think it also has some more practical implications as far as really understanding the role of clouds, which we still really don't understand, and understanding the role of surface atmosphere chemical interactions. You know, there's a lot of Earth theory that we apply to Venus in this sort of cartoon way that we'll be able to fill in with much more actual knowledge. And in turn, that will help us validate the ideas that we use, including the ideas that we use to understand long-term evolution of our own planet.